I've always wondered how Earth actually formed. About 4.5 billion years ago, our planet began as just dust and gas swirling around the young sun within the early solar system. Over time, tiny particles collided, stuck together, and grew into larger and larger bodies until one of them became the Earth we live on today. A dramatic collision with a Mars-sized object, often called Theia, likely helped shape the planet and even formed the Moon. In today's documentary, we'll see how Earth actually formed. Look at this world. From space, Earth appears as a jewel suspended in the darkness. Its blue oceans swirling with white clouds, its continents painted in browns and greens. Come closer now and watch as we descend through the atmosphere. See the rainforest teeming with millions of species, each one a masterpiece of biological engineering. Dive beneath the waves and discover coral reefs that host more diversity in a single square kilometre than exists on entire planets elsewhere in our solar system. Rise up over cities where billions of humans have built civilizations of staggering complexity. All of this exists on a ball of rock 25,000 miles in circumference, spinning through space at 67,000 miles per hour. But here's what should truly take your breath away. Every atom of every living thing you just saw, every drop of water in those oceans, every grain of sand on every beach, every mountain, every cloud, every bit of air you're breathing right now, all of it came from the same place. 4.5 billion years ago, none of this existed. Not the forests, not the oceans, not even the rock beneath your feet. Instead, there was only a cloud of gas and dust floating in the void of space, so diffuse that you could pass your hand through it and feel nothing at all. So how did we get from there to here? How did chaos become order? How did a cloud become a world? This is the story of the most extraordinary transformation in the history of our solar system. This is the story of how Earth was formed. And to understand it, we need to begin not 4.5 billion years ago, but much, much earlier. We need to begin at the very start of everything. The universe sets the stage. 13.8 billion years ago, our universe began with what we call the Big Bang. But we're not going to dwell on that moment of creation itself. Instead, I want you to think about what happened immediately after, because that's where our story truly begins. In the first 3 minutes after the Big Bang, as the universe cooled from temperatures beyond imagination, the first atomic nuclei formed. Protons fused together in the intense heat to create the nuclei of hydrogen, helium, and just a trace of lithium. That's it. Just 3 elements out of the 94 that occur naturally, and those 3 are the lightest and simplest on the periodic table. Now pause for a moment and look at your hand. The carbon in your DNA, the calcium in your bones, the iron in your blood, the oxygen you're breathing. Where did all of that come from? None of those elements existed yet. The early universe was essentially just hydrogen and helium gas, expanding and cooling. If the universe had stayed that way, nothing interesting would ever have happened. There would be no planets, no life, no one to tell this story. The fact that you exist at all means something else had to happen, some cosmic process that could forge heavier elements. That process is stellar nucleosynthesis, and it happens in the cores of stars. Think of stars as cosmic furnaces, gravitationally compressed to such extreme temperatures and pressures that atoms can be forced together against their natural repulsion. In the core of a star, hydrogen nuclei fuse into helium, releasing tremendous energy in the process. That's what makes stars shine. But here's where it gets interesting. When a star exhausts its hydrogen fuel, if it's massive enough, its core contracts and heats up even more, reaching temperatures where helium itself can fuse into carbon, then carbon can fuse with helium to make oxygen. In the most massive stars, this process continues through the periodic table, building up heavier and heavier elements. Silicon, sulfur, calcium, iron. But there's a limit. Iron is special because it's the most stable nucleus. Fusing iron doesn't release energy, it absorbs it. So when a massive star's core has converted to iron, the fusion process stops. Without the outward pressure from fusion to balance gravity's inward pull, the core collapses catastrophically in a fraction of a second. Then it rebounds in one of the most violent events in the universe, a supernova explosion. For a few weeks, a single dying star can outshine an entire galaxy containing hundreds of billions of stars. In that explosion, several things happen that are crucial for our story. First, the intense heat and pressure create elements even heavier than iron through rapid neutron capture, producing everything from cobalt up through uranium. Second, and this is the key point, the explosion scatters all those elements, everything the star created during its lifetime and in its death, out into space. The star dies, but it seeds the cosmos with the building blocks of planets and life. This is what we mean when we say you are made of stardust. It's not a metaphor or poetry. Every atom in your body, heavier than hydrogen, was literally forged inside a star that exploded before our sun even existed. The oxygen you just breathed was made in a star 8 times the mass of our sun, fusing helium in its core 6 billion years ago. The iron in your blood was synthesized in the final moments before a massive star collapsed into a supernova. The gold in any jewelry you might be wearing was created when 2 neutron stars, the remnant cores of dead stars, spiraled into each other and merged in a kilonova explosion, an event so energetic it warped the fabric of space-time itself. Generation after generation of stars lived and died, each one enriching the interstellar medium with heavier elements. The universe was slowly changing its chemical composition, transforming from the simplicity of hydrogen and helium into something far more interesting. By the time our story begins in earnest, about 4.6 billion years ago, the region of space that would become our solar system had been enriched by countless stellar generations. The ingredients for making planets and eventually life were finally in place. But they still needed to be assembled. And that's where we go next. Our solar neighborhood takes shape. Let me take you to a place and time very different from the Earth you know. We're in the Orion arm of the Milky Way galaxy, about 26,000 light-years from the galactic center. The time is 4.6 billion years ago. If you could stand here, which you couldn't because there's no here yet, you would find yourself inside a giant molecular cloud. This cloud is vast beyond comprehension, perhaps 100 light-years across, containing enough mass to make thousands of stars and their planetary systems. It's composed mostly of hydrogen and helium, the ancient legacy of the Big Bang, but mixed in are those heavier elements, that stardust, comprising perhaps 2% of the mass. It doesn't sound like much, but that 2% will make all the difference. The cloud is cold, just a few tens of degrees above absolute zero, and extraordinarily diffuse. If you could hold out a container the size of a milk bottle, you might capture a few thousand molecules. That's a vacuum far better than anything we can create in laboratories on Earth. The cloud is dark too, because dust particles mixed with the gas block visible light. If you could see it from outside, it would appear as a dark nebula, a shadow against the backdrop of stars. But this cloud is not going to remain peaceful. Something is about to disturb its equilibrium. Perhaps it's the shockwave from a nearby supernova, that same supernova that enriched this region with heavy elements in the first place. Perhaps it's the gravitational influence of a passing star, or the cloud simply reaches a critical density where its own gravity overcomes the pressure supporting it. Whatever the trigger, a portion of this cloud, a region perhaps 1 light-year across, begins to collapse. As it collapses, gravity pulls material toward the center, and conservation of angular momentum, the same physics that makes a figure skater spin faster when they pull in their arms, causes the cloud to rotate faster and faster. The collapsing material can't all fall straight to the center because of this rotation. Instead, it forms a disk, like pizza dough being spun by a chef. Material in the center collapses into a dense, hot core that will become our sun. But surrounding it is a flattened disk of gas and dust called a protoplanetary disk. And this is where Earth and all the other planets will be born. Let me help you visualize this disk, because understanding its structure is crucial for everything that follows. The disk extends billions of miles from the young sun at its center. Close to the sun, temperatures are scorching, perhaps 1500 degrees Kelvin. Only materials that can survive those temperatures remain solid here, primarily metals like iron and rocky minerals like silicates. Any water, methane, ammonia, or other volatile compounds that might have been present have been vaporized and blown outward by the intense radiation and stellar wind from the young sun. But as you move farther from the sun, temperatures drop. Beyond a certain distance, which astronomers call the frost line or snow line, located somewhere around where the asteroid belt is today, temperatures fall below the freezing point of water. Out here, ice can exist. This means there's simply more solid material available to build planets in the outer solar system compared to the inner solar system. That's why the outer planets, Jupiter, Saturn, Uranus and Neptune, grew to be giants while the inner planets remained relatively small. The disk is not uniform. It has turbulence and eddies, regions of higher and lower density. And within this disk, slowly at first but accelerating over time, the process of planet formation is beginning. Dust particles are colliding and sticking together. This is where Earth's journey truly begins. not as a planet yet, but as microscopic specks of dust tumbling through a disk of gas, each one beginning the long journey toward becoming part of something greater. From dust to planetesimals. Now we need to shrink our perspective dramatically. Forget the vast scale of the protoplanetary disk for a moment. I want you to focus on something almost too small to see. A dust grain floating in this disk, perhaps a micrometer across, smaller than a red blood cell. This grain is made of minerals, perhaps a silicate particle similar to sand, or maybe a tiny fleck of iron. It's tumbling slowly through space, occasionally bathed in the faint light of the young sun, barely visible through the dusty fog. This particle is on a journey, though it has no way of knowing it. As it drifts through the disk, it occasionally encounters another dust grain. Most of the time, they simply bounce off each other and continue on their separate ways. But sometimes, just sometimes, they stick. The reasons for sticking are varied. In the inner solar system where Earth will form, electrostatic forces, essentially static electricity, can cause grains to adhere. In the colder outer regions beyond the frost line, ice acts as a glue, binding particles together. Surface forces at the molecular level also play a role. The physics of how the very first sticking occurs is actually still debated by planetary scientists, but stick they do. One grain becomes two grains stuck together, then three, then a dozen. We're building an aggregate now, a fluffy structure like a dust bunny, full of empty space between the individual grains. This aggregate has a larger cross-section, so it sweeps up more material as it moves through the disk. The growth is slow at first, agonizingly slow. It might take thousands of years to grow from a micrometer to a millimeter to reach the size of a grain of sand. But as particles grow larger, gravity begins to play a role. Once objects reach about a kilometer in size, their own gravity becomes significant enough to help them attract other objects nearby. At this point, growth accelerates dramatically. We're no longer just relying on chance collisions. Objects are gravitationally focusing material toward themselves, sweeping up everything in their orbital path. These kilometer-sized objects are called planetesimals, and they're the building blocks of planets. The protoplanetary disk is now a shooting gallery of colliding planetesimals. Some collisions are gentle enough that the objects merge, growing larger. Other collisions are so violent that both objects shatter, sending fragments cascading through the disk. It's a chaotic, violent process, but out of this chaos, order emerges. The largest planetesimals in any region of the disk have a huge advantage. Because they're more massive, their gravity is stronger, so they attract more material. They grow faster, which makes them even more massive, which makes them grow even faster still. It's a runaway process, the rich getting richer. In the region where Earth is forming, about 93 million miles from the Sun, dozens of planetesimals are competing for dominance. Over hundreds of thousands of years, this competition plays out. Smaller planetesimals are either consumed by larger ones or ejected from the region entirely through gravitational interactions. Eventually, perhaps after about 100,000 years from when dust first started sticking together, a handful of Moon-to-Mars-sized objects dominate the inner solar system. These are called planetary embryos, and they're the immediate precursors to the rocky planets we know today. One of these embryos, orbiting in the zone we now call Earth's orbit, is pulling ahead of its competitors. It's growing larger and larger, its gravity reaching farther and farther, capturing more and more of the remaining planetesimals. This is Proto-Earth, and it's about to undergo a transformation more violent than anything the Earth experiences today. To understand what happens next, we need to appreciate just how energetic planetary formation really is. Every time a planetesimal crashes into the growing Proto-Earth, its energy of motion, its kinetic energy, converts to heat. Remember that these objects aren't drifting gently together. They're moving at orbital velocities, many kilometers per second. An impact at those speeds releases as much energy per kilogram as a large chemical explosive. And there are millions upon millions of these impacts, ranging from pebbles to objects hundreds of kilometers across. All that energy has to go somewhere, and most of it goes into heat. Proto-Earth is not the cool, solid world we know today. It's a molten ball of rock, its surface a magma ocean thousands of kilometers deep, glowing orange and red like a coal in a furnace. The heat is so intense that rock vaporizes on impact, creating an atmosphere of rock vapor that glows incandescently. This is a hellscape beyond imagination, a world that would be unrecognizable as Earth. But it's a necessary stage. This molten state allows something crucial to happen, something that will define Earth's structure for the rest of its existence. The planet is differentiating. The birth of Proto-Earth. Imagine taking a pot of soup that contains chunks of different ingredients, vegetables, meat, noodles, all mixed together, and heating it until everything melts into a liquid. Then imagine that some ingredients are denser than others. The dense ingredients would sink to the bottom, while the lighter ones float to the top. This is essentially what's happening inside the molten Proto-Earth, except instead of soup, we're talking about an entire planet. And instead of minutes, this process takes millions of years. The material making up Proto-Earth isn't uniform in composition. Remember that planetesimals formed from dust that originally condensed in the protoplanetary disk, and that dust contained both rocky silicate minerals and metallic iron and nickel. Initially, these materials were mixed together as planetesimals accreted. But now, with the entire planet molten, gravity can sort them. Iron is almost twice as dense as typical silicate rock. In the molten state, droplets of liquid iron begin sinking toward the center of the planet, pulled by gravity. This process, called the iron catastrophe, releases even more gravitational potential energy, further heating the planet. It's a runaway process. The iron sinks faster as the planet heats up, and the sinking iron releases more heat. Over perhaps 10 million years, most of the iron in Proto-Earth migrates to the center, forming a dense metallic core. The rocky material, composed primarily of silicates rich in magnesium, silicon, oxygen, and other lighter elements, is left behind to form the mantle surrounding the core. The very lightest materials, including minerals rich in aluminum and silicon, float to the top to form a primitive crust when and if the surface cools enough to solidify. This layered structure, with a dense iron core, a rocky mantle and a thin crust, is the basic architecture that Earth maintains to this day. You're living on the skin of a differentiated planet, standing on rock that floats on a mantle that surrounds a metallic core. But proto-Earth is not finished forming. It's grown to perhaps 90% of Earth's current mass, but there's still a lot of debris in Earth's orbital zone, and the accretion process continues. The impacts continue too, though they're becoming less frequent as the solar system cleans itself up. Still, when impacts do occur, they can be spectacular. Some of the remaining planetary embryos are large objects, and when one of those hits proto-Earth, the entire planet rings like a bell. Magma oceans slosh across the surface and vaporized rock blasts into space. Now I need to tell you about the most important collision in Earth's history, an impact so consequential that it shaped not only Earth, but created an entirely new world. We're about to witness the birth of the moon-forming impact. It's roughly 4.5 billion years ago. Proto-Earth has been growing for perhaps 50 million years and has achieved nearly its current mass. The magma ocean on its surface has begun to cool, at least in some places, forming a temporary crust that constantly breaks apart and reforms as impacts continue to pummel the surface. The bombardment is lessening, though, as the planet sweeps up most of the debris in its orbital zone. But there's another planetary embryo sharing Earth's general neighborhood, orbiting the Sun somewhere nearby. Astronomers have given this object a name, though of course it had no name at the time. They call it Theia, after the mother of the moon goddess Selene in Greek mythology. Theia is substantial, perhaps 10 to 15% of Earth's mass, roughly the size of Mars. For millions of years, Theia and proto-Earth have coexisted, their orbits shaped by mutual gravitational interactions and the influence of Jupiter farther out. But orbital dynamics are chaotic over long timescales. Small perturbations accumulate. Eventually the orbits of Theia and proto-Earth intersect. They're on a collision course. Imagine watching this from a safe distance, though there is no safe distance really. Theia approaches Earth not head-on, but at an oblique angle, striking Earth's equator at perhaps a 45-degree angle from vertical. The relative velocity at impact is something like 4 kilometers per second, about 9,000 miles per hour. At this speed, matter doesn't behave like solid rock anymore. It behaves almost like a fluid. The impact is so violent that both Theia and a significant portion of proto-Earth's mantle simply vaporize. Imagine taking two enormous balls of rock and metal and converting a substantial fraction of their mass instantly into vapor at temperatures of tens of thousands of degrees. The shock wave from the impact propagates through proto-Earth's entire volume, melting rock that had begun to solidify, churning the mantle, possibly even affecting the core. But here's the crucial detail about this impact. Because Theia struck at an angle rather than head-on, it imparted tremendous angular momentum to the Theia system. Think of it like a glancing blow in billiards that sets the target ball spinning. Material from both bodies, mostly from their rocky mantles because the collision happened before both objects were fully differentiated, is blasted into orbit around Proto-Earth. The cores of both bodies, being denser and deeper, mostly survive the impact and merge, sinking to form Earth's core as we know it. The orbiting debris forms a massive disk around Earth, similar in concept to the rings of Saturn, but far more substantial. This disk is composed of molten rock and vapor, glowing from its own heat. Over a remarkably short time, perhaps less than a century, this debris begins to coalesce under its own gravity. The material nearest to Earth rains back down onto the planet, adding to its mass. But material farther out, beyond the Roche limit, where tidal forces from Earth no longer tear apart large objects, can accrete into a single body. The moon is born. The early moon is very different from what you see in the sky tonight. It forms much, much closer to Earth, perhaps just 15,000 miles away compared to the current 250,000 miles. From Earth's surface, if there were anyone to see it, the moon would loom enormous in the sky, perhaps 20 times larger in apparent size than it appears today. The tidal forces between Earth and Moon are tremendous, potentially raising tides in Earth's magma ocean hundreds of meters high. Both bodies are still largely molten, heated by the impact and by the tidal kneading they inflict on each other. But the moon-forming impact did more than just create Earth's satellite. It had profound consequences for Earth itself. First, it likely tilted Earth's rotation axis to its current 23.5-degree angle relative to its orbital plane. This tilt gives us our seasons, and without it, Earth's climate would be very different. Second, the impact thoroughly mixed and homogenized Earth's mantle, which affects the planet's subsequent geological evolution. Third, the impact delivered additional material to Earth, and some planetary scientists think Theia might have come from farther out in the solar system where water ice was common, potentially delivering a significant fraction of Earth's water. Most importantly, for Earth's long-term habitability, the Moon itself plays a crucial role. The Moon's gravitational pull creates tides in Earth's oceans, which even today help drive ocean mixing, and may have been important for the origin of life. More subtly, the Moon stabilizes Earth's axial tilt over billion-year timescales. Computer simulations show that without the Moon, Earth's tilt would vary chaotically from near zero to 85 degrees over millions of years, causing wild climate swings that might have prevented complex life from evolving. Mars, which lacks a large stabilizing moon, experiences exactly this kind of chaotic obliquity variation. In a very real sense, the Moon is Earth's partner, and we owe our existence to a random collision 4.5 billion years ago. If Theia had been slightly smaller, or had hit at a different angle, or had missed Earth entirely, the world you live on would be fundamentally different, and you might not be here to contemplate it. But our story of planetary formation is not over. The giant impact that formed the Moon remelted Earth's surface, erasing whatever progress had been made toward a stable crust. For millions of years after the impact, Earth remains a magma-covered hell world, slowly radiating heat to space, slowly cooling, attempting once again to form a solid surface. And just as that surface begins to solidify, just as Earth seems ready to transition from a world of fire to something more stable, disaster strikes again. The Late Heavy Bombardment. For about 500 million years after the moon-forming impact, the solar system settles into an uneasy calm. Earth's surface finally cools enough to form a solid crust, though volcanoes constantly break through, erupting magma from the still molten mantle below. The bombardment continues, but at a declining rate as the planets sweep up most of the debris in their orbital zones. Water vapor in the atmosphere begins to rain out, forming Earth's first oceans, though we'll discuss that process in detail shortly. Some scientists think life might have even originated during this period. If so, what happens next wiped it out completely. Something catastrophic occurs in the outer solar system roughly 4 billion years ago. The details are still debated, but the leading theory is that Jupiter and Saturn, the two most massive planets, drift slightly in their orbits due to interactions with remaining debris in the outer solar system. As they drift, they fall into what's called an orbital resonance, where Jupiter completes exactly 2 orbits for every 1 orbit of Saturn. This might sound like a minor detail, but orbital resonances can have dramatic effects. The gravitational perturbations from this resonance destabilize the orbits of countless icy bodies beyond Saturn. These objects, which had been peacefully orbiting the Sun for hundreds of millions of years, suddenly find their orbits becoming elliptical and chaotic. Some are ejected from the solar system entirely. Others plunge inward toward the Sun, crossing the orbits of the inner planets. Earth, along with the other terrestrial planets and the Moon, is pummeled by this renewed bombardment. We call this the Late Heavy Bombardment, and the evidence for it is written across the face of the Moon. Look up at the Moon tonight, and the dark regions you see, the Lunar Maria, are actually vast impact basins filled with solidified lava. Most of these basins, with names like Mare Imbrium and Mare Serenitatis, were created during the Late Heavy Bombardment by impactors tens or even hundreds of kilometers in diameter. On Earth, the effects would have been even more dramatic, because Earth is a bigger target with stronger gravity, attracting more impacts. Picture an impact by an object 50 kilometers across, about the size of the asteroid that killed the dinosaurs, but arriving at even higher velocity. The impactor hits with such energy that it vaporizes instantly, along with a massive volume of the crust where it hits. A fireball expands at supersonic speed, flattening everything in its path for thousands of kilometers. Vaporized rock blasts into the atmosphere and rains back down as molten droplets, potentially heating the entire surface to oven-like temperatures. If Earth had oceans by this point, the upper layers might have been boiled away by the largest impacts. For perhaps 1 to 200 million years, Earth endures this renewed bombardment. Any progress toward habitability is repeatedly set back. If life had originated in the earlier, quieter period, it might have survived only in the deepest ocean vents or in pores deep within the crust. protected from the devastation above. The late heavy bombardment was a time of destruction, a cosmic reset button that nearly sterilized Earth multiple times over. But here's a fascinating twist to this story. Those impactors raining down from the outer solar system weren't made of rock like the planetesimals that built Earth. They were made largely of ice, water ice, and other frozen volatiles like methane and ammonia mixed with rock. When they crashed into Earth, they delivered their volatile cargo. Each impact that brought destruction also brought precious cargo for the future. It brought water. This leads us to one of the great questions about Earth's formation. Where did Earth's water come from? The region where Earth formed was hot, above the freezing point of water, so any water-rich material should have been vaporized and blown away by the young sun's radiation. Early Earth probably formed relatively dry. Yet today, Earth's surface is 70% covered by oceans averaging 4 kilometers deep. That's a lot of water that had to come from somewhere. For decades, scientists have debated whether Earth's water was delivered by comets from the outer solar system, by water-rich asteroids from beyond the frost line, or whether some water was present in the minerals that formed Earth and was later released through volcanic outgassing. Recent measurements comparing the isotopic composition of Earth's water with water in various types of meteorites suggest that much of our water probably came from carbonaceous asteroids, primitive rocky bodies from the outer asteroid belt that contain up to 10% water by weight. The late heavy bombardment would have delivered enormous quantities of these water-bearing asteroids to Earth. It's one of the great ironies of Earth's history. The same cosmic catastrophe that destroyed whatever surface conditions existed also delivered the very substance that would make Earth habitable. After the chaos comes the possibility of life. Once the late heavy bombardment finally ends, around 3.8 billion years ago, Earth can begin the transition from a world of fire and bombardment to something more peaceful, more stable, more familiar. The stage is set for Earth to become the water world we know today. The atmosphere's first breath. As the late heavy bombardment tapers off, Earth finally has the opportunity to develop persistent surface conditions. The crust has solidified, though it's still frequently broken by volcanic activity. The planet's interior remains extremely hot, a legacy of the energy from all those impacts and from the radioactive decay of elements like uranium and thorium in Earth's mantle and crust. This heat drives volcanism on a scale difficult to imagine today. Picture the surface of this ancient Earth. Vast volcanic fields stretch to the horizon, with thousands of volcanoes actively erupting. Lava floods across the landscape, building up layer upon layer of basaltic rock. The sky glows red from the reflected light of molten rock. And from these volcanoes, from every fissure and vent in the crust, gases pour forth. This is outgassing, and it's the process that creates Earth's first true atmosphere. What gases are these volcanoes releasing? We can get some idea by studying volcanic gases today, though Earth's early volcanoes were probably even more gas-rich than modern ones. The dominant gas is water vapor, steam from water that was trapped in minerals in the mantle and is now being released. Carbon dioxide is abundant too, along with nitrogen, sulfur dioxide, and smaller amounts of hydrogen, methane, ammonia, and other gases. What's almost entirely absent, and this is crucial, is free oxygen. There's essentially no O2 in this early atmosphere. The atmosphere builds up gradually as volcanism continues over millions of years. Eventually, it becomes substantial enough to create significant pressure at the surface, perhaps similar to or even greater than the atmospheric pressure we experience today. This atmospheric pressure is important because it raises the boiling point of water, allowing liquid water to exist at the surface even when temperatures are relatively high. The composition of this atmosphere shapes Earth's early climate in profound ways. Carbon dioxide is a greenhouse gas, meaning it traps infrared radiation and warms the surface. This is actually extremely important for early Earth because the young sun was about 30% dimmer than it is today. Without greenhouse gases to trap heat, Earth should have been frozen solid, with the surface temperature well below the freezing point of water. This puzzle, called the faint young sun paradox, is resolved by recognizing that Earth's early atmosphere was much richer in greenhouse gases than today's atmosphere. The abundance of carbon dioxide, possibly supplemented by methane and other greenhouse gases, created enough warming to keep Earth's surface above freezing despite the dim sun. It's a delicate balance. Too little greenhouse gas and Earth freezes. Too much and it becomes a runaway greenhouse like Venus, where temperatures are hot enough to melt lead. Earth threads the needle, maintaining conditions where water can exist as a liquid. And now, finally, we come to one of the most beautiful transitions in Earth's history. The water vapor in the atmosphere, so abundant from all that volcanic outgassing, begins to cool. As it cools, it condenses into droplets. Clouds form, thick and dark, covering the entire planet. The temperature drops below the dew point, and then, for the first time in Earth's history, it starts to rain. The first oceans. Imagine rain falling continuously, not for days or weeks or even months, but for thousands, perhaps millions of years. Every drop that falls is a drop that's never fallen before, because this is water that's been locked in the mantle since Earth formed, now seeing the surface for the first time. The rain is warm, almost hot, because the atmosphere and surface are still far above modern temperatures. It's acidic too, because it's absorbed carbon dioxide and sulfur dioxide from the atmosphere, forming weak solutions of carbonic and sulfuric acid. The rain falls on a landscape of bare volcanic rock, dark basalts, and other igneous rocks with no soil, no vegetation, nothing to slow the water's rush across the surface. It collects in every depression, every crater, every valley, and begins to flow downhill, carving channels as it goes. The water accumulates in the lowest places, the impact basins and tectonic depressions, forming the first lakes and seas. As more rain falls and more volcanic outgassing continues, these bodies of water grow deeper and begin to merge. Over geologic time, perhaps 10 million years, perhaps longer, a global ocean forms. This ocean is nothing like the clear blue waters you see today. It's cloudy with suspended sediments, possibly tinted green or brown from dissolved iron, which is abundant on the surface before oxygen exists to rust it. The water is warm, possibly approaching boiling in some locations near volcanic vents. And it's acidic from all the dissolved atmospheric gases. But this ocean, primitive as it is, changes everything about Earth. Water is an incredibly effective solvent and chemical mediator. It begins to chemically weather the rocks it touches, breaking down minerals and carrying dissolved ions into the ocean. This weathering process actually removes carbon dioxide from the atmosphere because CO2 dissolved in rainwater reacts with rocks containing calcium and magnesium, forming carbonates that precipitate out in the ocean. Here's one of the first feedbacks in Earth's climate system. If too much CO2 builds up, warming Earth, the water cycle intensifies, weathering increases, and more CO2 gets removed, cooling things back down. The ocean also moderates temperature more effectively than land. Water has a high heat capacity, meaning it takes a lot of energy to change its temperature. The ocean can absorb heat during the day and release it at night, during summer and winter, smoothing out temperature extremes. This makes Earth more temperate, more stable, more hospitable. Beneath the ocean's surface, the water is in direct contact with the hot crust. In places where volcanic activity is particularly intense, seawater seeps down through cracks in the rock, gets heated by magma beneath, becomes buoyant, and rises back up, emerging as hydrothermal vents. If you've seen video from modern submarine exploration, you might have seen these vents, chimneys of mineral deposits called black smokers, where superheated water, rich in dissolved minerals and gases, billows out into the cold ocean water. These vents exist on early Earth too, and many scientists think they might have been the crucibles where life first originated. Think about what these vents provide. You have liquid water, obviously necessary for life as we know it. You have chemical energy because the minerals and gases dissolved in the vent fluid are out of chemical equilibrium with the surrounding seawater, and life is fundamentally about exploiting chemical disequilibrium. You have mineral surfaces, which could act as catalysts for chemical reactions or templates for organizing organic molecules. And you have protection from the hostile conditions on the surface, from UV radiation and impacts. The ocean also creates an enormous volume for chemistry to occur. In solid rock, molecules are locked in place. In the thin atmosphere, molecules are spread out and collisions are rare. But in the ocean, molecules are concentrated yet mobile, constantly colliding and reacting. The ocean is nature's laboratory, a place where chemistry can explore possibilities on a planetary scale. We're now about 4 billion years ago, give or take a few 100 million years. The late heavy bombardment has ended. Earth has a solid crust, a thick atmosphere, and a global ocean. The surface temperature is still warm, perhaps averaging 50 or 60 degrees Celsius compared to the modern 15 degrees, but it's stable. Water is liquid. Chemistry is happening. The stage is set for the next great transition in Earth's history, and it might have already begun in those deep ocean vents. The transition from geology to biology, from a world of rock and water to a living world. But before life can emerge, before biology becomes possible, Earth's interior needs to organize itself into a system that will support a habitable surface for billions of years. The planet needs to become geologically active in a very specific way. It needs to develop plate tectonics. Plate tectonics awakens. Stand on the ground beneath your feet and consider what's below you. You're standing on a rigid plate of rock, Earth's crust, that's perhaps 30 kilometers thick if you're on a continent, or just 7 kilometers thick if you're under the ocean. Below that is the mantle, nearly 3,000 kilometers of hot solid rock that nonetheless flows slowly over geologic time, like picture glass. And at the center is the core, divided into a liquid iron outer core and a solid iron inner core. This structure, remember, came about through differentiation when Earth was molten. But here's what makes Earth special compared to other rocky planets. Earth's interior has stayed hot enough, and its mantle has stayed just the right viscosity to drive a process that's unique in our solar system. Earth's crust is broken into about a dozen major plates and several smaller ones, and these plates are constantly moving, driven by slow convection currents in the mantle below. Let me help you understand what's happening. The mantle is heated from below by the core and by radioactive decay of elements within the mantle itself. Hot rock at the base of the mantle becomes buoyant and rises slowly over millions of years toward the surface. As it approaches the surface, it cools, becomes denser, and eventually sinks back down. This creates convection cells, similar in principle to the way water circulates in a pot on the stove, though vastly slower. The solid rock of the mantle flows at rates of a few centimeters per year, about as fast as your fingernails grow. This mantle convection drags on the base of the overlying crust, and because the crust is brittle rather than plastic like the mantle, it breaks into plates. The plates move with the convection currents, traveling at those same fingernail growth rates across Earth's surface. Where hot mantle material rises, new oceanic crust forms at mid-ocean ridges. Where plates collide, one plate dives beneath the other in a process called subduction, and the descending plate eventually melts back into the mantle. Where plates slide past each other, you get transform faults and earthquakes. Now, you might reasonably ask, why does this matter? Why is plate tectonics important for Earth's story and for life? The answer has several parts, and each one is crucial. First, plate tectonics creates topographic diversity. When plates collide, they build mountain ranges like the Himalayas. When they pull apart, they create ocean basins and rift valleys. This diversity of elevations creates diverse climate zones and habitats. It creates ecological niches that can be filled by different forms of life. Second, plate tectonics drives volcanism, and volcanism recycles gases from Earth's interior to the atmosphere. Without this recycling, carbon dioxide would gradually be removed from the atmosphere through weathering and locked up in rocks on the ocean floor. Eventually, the greenhouse effect would weaken, Earth would cool, and the planet would freeze. But subduction takes those carbon-rich rocks and drags them back down into the mantle. At depth, they heat up, and the carbon is released as CO2 through volcanic eruptions, returning to the atmosphere. This creates a geological thermostat, a feedback mechanism that has kept Earth's climate relatively stable for billions of years. Third, and this is more subtle, plate tectonics creates chemical diversity. When oceanic crust subducts, it carries water with it into the mantle, and that water helps melt the rock above it, creating magma that rises to form volcanic arcs. This process creates a wider variety of rock types and minerals than would exist without plate tectonics. That chemical diversity may have been important for life's origin and evolution. And fourth, plate tectonics efficiently cools Earth's interior. Unlike the Moon or Mars, which have thick, stagnant outer layers that insulate their interiors, Earth constantly recycles its crust, allowing heat to escape from the deep interior. This keeps the outer core molten and convecting, and that convection generates Earth's magnetic field, the magnetic shield that protects our atmosphere from the solar wind. When did plate tectonics begin on Earth? This question is actively debated by geologists. Some think it started quite early, perhaps within the first few 100 million years of Earth's history. Others think it took longer for the interior to cool to the right temperature and for the crust to thicken enough to fracture into plates. The evidence from ancient rocks suggests that something like modern plate tectonics was definitely operating by 3 billion years ago, and possibly earlier. What's certain is that by the time we're discussing now, around 4 billion years ago, Earth's interior is organized into a heat engine that will keep the surface dynamic for billions of years to come. The plates are moving, continents are forming and breaking apart, oceans are opening and closing. Earth is not a static stage on which life's drama will play out. Earth itself is dynamic, constantly changing, and that dynamism will profoundly influence the evolution of life. But we're getting ahead of ourselves. Before we can talk about how life evolves, we need to address the greatest mystery in Earth's history. How did life begin in the first place? The magnetic shield. Before we turn to the origin of life, there's one more piece of Earth's protective infrastructure we need to understand. Deep within our planet, nearly 3,000 kilometers below the surface, something remarkable is happening that you've probably never thought about, but which is absolutely essential for your existence. The temperature at the boundary between Earth's mantle and outer core is approximately 4,000 degrees Celsius, hot enough to melt iron and nickel. Below this boundary, the outer core is indeed molten, a churning ocean of liquid metal 2,000 kilometers thick. But at the very center, at Earth's inner core, the pressure is so immense, over 3 million times atmospheric pressure, that despite temperatures exceeding 5,000 degrees, the iron is compressed into a solid sphere about the size of the Moon. This structure, a solid inner core surrounded by a liquid outer core, creates the conditions for something extraordinary. The liquid iron in the outer core is electrically conductive, and it's in constant motion, stirred by convection currents as heat escapes from the inner core and by the rotation of the planet. When you have a moving electrical conductor, you generate magnetic fields. This is the same principle that makes an electric generator work, and Earth's core is essentially a planet-sized dynamo, converting mechanical energy into magnetic energy. The magnetic field generated by this process extends far beyond Earth's surface, stretching tens of thousands of kilometers into space and creating a region called the magnetosphere. You can't see it or feel it directly, but it's there, invisible lines of magnetic force wrapping around the planet like a protective cocoon. And you should be very grateful it exists, because without it, Earth would be a very different place. The sun is not just a source of light and heat. It's also constantly streaming charged particles into space, what we call the solar wind. These particles, mainly electrons and protons, travel at speeds of hundreds of kilometers per second. When they encounter Earth, they don't just bounce off harmlessly. Without a magnetic field, they would strike the upper atmosphere directly. Over time, the energy from these particles would strip away atmospheric molecules, essentially sandblasting the atmosphere into space. This isn't theoretical speculation. We can observe this process happening right now on Mars. Mars once had a magnetic field generated by its core, but about 4 billion years ago, the Martian core cooled enough that the dynamo shut down. The magnetic field disappeared, and over the subsequent billions of years, the solar wind has stripped away most of Mars's atmosphere. What was once a world with a thick atmosphere and liquid water on its surface is now a frozen desert with an atmosphere less than 1% as dense as Earth's. Earth's magnetic field prevents this fate. The magnetosphere deflects most of the solar wind around Earth, channeling it past us rather than letting it strike the atmosphere. Some particles do leak through, particularly near the magnetic poles, and when they collide with atmospheric molecules, they create the aurora borealis and aurora australis, the northern and southern lights. These beautiful light displays are actually evidence of the magnetic field protecting us, showing us where particles are funneling down along the field lines into the upper atmosphere. But the magnetic field does more than just protect the atmosphere in general. It specifically protects the ozone layer in the upper atmosphere, and the ozone layer blocks harmful ultraviolet radiation from the sun. Without this double protection, magnetic field protecting ozone and ozone protecting the surface, life on Earth's surface would be nearly impossible. Early life that arose in the oceans was protected by water, which blocks UV radiation. But when life eventually moved onto land, about 400 million years ago, it could only do so because Earth's magnetic field had preserved an atmosphere thick enough to maintain an ozone layer. Think about the chain of connections here, because this is how Earth works as a system. The planet formed large enough that its interior is still hot after 4.5 billion years. That heat drives convection in the liquid outer core. That convection generates a magnetic field. That magnetic field protects the atmosphere from erosion. That atmosphere shields the surface from radiation. And that protection makes the surface habitable for complex life. Remove any link in this chain, and Earth becomes a very different world. This is why planetary scientists talk about Earth being in the Goldilocks zone, not just in terms of distance from the Sun, but in terms of a whole suite of properties that all had to be just right. Earth had to be the right size to stay geologically active. It had to differentiate to form a metallic core. That core had to stay partially molten. The mantle convection had to be vigorous enough to drive plate tectonics. Every piece matters, and Earth somehow got all of them right. Now, with all these protective systems in place, with a magnetic shield guarding the atmosphere, with plate tectonics recycling materials and regulating climate, with oceans providing a medium for chemistry and temperature regulation, Earth is ready. The stage is fully set for the most important development in planetary history, the emergence of life, the first spark. Here we stand at the greatest mystery in science, a question that has puzzled humanity for as long as we've been capable of asking questions. How did non-living matter become living? How did chemistry become biology? At what moment did a collection of molecules first deserve to be called alive? The honest answer is that we don't know for certain. We weren't there to witness it, and life's origin left behind almost no direct evidence. The earliest rocks that might preserve fossils have been so altered by heat and pressure over billions of years that any traces of ancient life have been erased or rendered ambiguous. But we can make educated inferences based on what we know about chemistry, about early Earth's conditions, and about the basic requirements for life. Let's start with what life needs at minimum. All life we know requires liquid water as a solvent for biochemistry. Life needs a source of energy to drive chemical reactions uphill against entropy. Life needs the raw materials to build itself, specifically organic molecules containing carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. And crucially, life needs some way to store and transmit information so that it can reproduce and evolve. In modern life, that information storage is handled by DNA and RNA, but the very first life was probably much simpler. So where and when did life begin? The when is uncertain but constrained. Life certainly couldn't have originated during the late heavy bombardment, when impacts repeatedly sterilized the surface. But there's tantalizing, controversial evidence in rocks from Greenland that might be chemical signatures of life dating to 3.8 billion years ago, right after the bombardment ended. If that evidence holds up, it means life appeared remarkably quickly once conditions stabilized. This suggests that perhaps the origin of life isn't as difficult or unlikely as we might fear. Given the right conditions, given liquid water and chemical energy and organic molecules, life might be almost inevitable. As for the where, scientists have proposed several possibilities, and the debate continues. The classic hypothesis involves shallow tidal pools or hot springs, where water evaporates and concentrates organic molecules, and where cycles of wetting and drying might help molecules polymerize into longer chains. Charles Darwin himself speculated about life beginning in a warm little pond. But there are problems with this scenario, particularly the intense UV radiation that would have bombarded any shallow water on early Earth before the ozone layer existed. A more popular modern hypothesis focuses on those hydrothermal vents we mentioned earlier, particularly a type called alkaline vents, or white smokers. These vents form where seawater percolates through the crust, gets heated and chemically altered by reactions with minerals, and then seeps back out. Unlike black smokers, which are extremely hot, alkaline vents are moderate in temperature, perhaps 40 to 90 degrees Celsius, warm but not boiling. The fluid emerging from these vents is alkaline, basic rather than acidic, and it's rich in hydrogen gas and dissolved minerals. Here's why these vents are compelling as a site for life's origin. The mixing of alkaline vent fluid with the more acidic ocean water creates natural chemical gradients across the porous mineral structures of the vent. These gradients can drive chemical reactions, providing energy without the need for sunlight. The porous mineral chambers provide compartments that could concentrate organic molecules and protect fragile chemistry from being diluted in the vast ocean. Some of the minerals in these vents, particularly iron and nickel sulfides, can act as catalysts for organic reactions. Remarkably, these same metals are found at the active sites of many enzymes in modern cells, hints of a possible ancient connection. But however life started, wherever it started, we know something profound about what it was like. The last universal common ancestor of all life on Earth, often abbreviated as Luca, lived sometime before 3.5 billion years ago. We can infer properties of Luca by looking at what all modern life shares, the biochemical features that are universal. And what we find is surprising. Luca was not the first life. It was already fairly sophisticated, with DNA for information storage, RNA for transferring that information, proteins for doing cellular work, and a membrane to separate itself from the environment. It had metabolism, biochemical pathways for extracting energy and building cellular components. This means the origin of life itself, the very first self-replicating molecules, must have been even earlier and simpler than Luca. Perhaps life began with RNA molecules, or something similar that could both store information like DNA and catalyze reactions like proteins. These molecules could make imperfect copies of themselves using raw materials in the environment. Any variants that copied themselves more efficiently would become more numerous. That's natural selection at its most basic, and it requires no foresight or purpose, just chemistry and statistics. Over time, perhaps millions of years, evolution would favor molecules that became better at replicating, better at gathering resources, better at protecting themselves. Membranes would evolve to create distinct cells. Metabolism would become more sophisticated, allowing cells to exploit more diverse energy sources. Eventually, one lineage would give rise to Luca, and from Luca, all subsequent life on Earth would descend. Every bacterium, every plant, every animal, every fungus, every one of us, we're all cousins, separated by 3.5 billion years of evolution, but ultimately family, sharing the same ultimate ancestor. But here's what's most important for Earth's story. Early life was entirely microbial, single-celled organisms far too small to see. And for nearly 2 billion years, from about 3.8 to 2 billion years ago, life remained exclusively microbial. These organisms lived in the oceans, possibly in the soil, if anything we could call soil existed yet. They extracted energy in various ways, some through chemicals, some eventually through sunlight. They reproduced and evolved and competed for resources. But they were doing something else too, something that would eventually transform Earth completely. They were changing the chemistry of the planet. Life was no longer just living on Earth. Life was beginning to alter Earth itself, setting up the next great transition in planetary history. An event so consequential that we call it the Oxygen Revolution. The Oxygen Revolution. For the first 2 billion years of life's existence on Earth, the atmosphere contained almost no free oxygen. There was water vapor, carbon dioxide, nitrogen, traces of methane and other gases, but oxygen gas, O2, was vanishingly rare. Any oxygen that formed through chemical processes, like ultraviolet light-splitting water molecules in the upper atmosphere, would quickly react with reduced minerals in the crust or with dissolved iron in the oceans, rusting them and removing the oxygen from circulation. Early life was adapted to this oxygen-free or anoxic world. Many organisms were what we call anaerobes, meaning they don't need oxygen and may actually be poisoned by it. These organisms extracted energy from chemical reactions that don't involve oxygen, like fermentation or methanogenesis, the production of methane gas. Life was constrained by the efficiency of these metabolisms, which yield far less energy than oxygen-based respiration. This energy limitation may be why life remained simple and single-celled for so long. But sometime around 3 billion years ago, perhaps earlier, a group of bacteria evolved a remarkable capability. They developed photosynthesis, the ability to capture energy from sunlight and use it to convert carbon dioxide and water into organic sugars, releasing oxygen as a waste product. These bacteria were the ancestors of modern cyanobacteria, and they look similar too, likely forming chains of cells or mats on the seafloor in shallow sunlit waters. This innovation was revolutionary in two ways. First, it tapped into an essentially unlimited energy source. The sun delivers more energy to Earth in an hour than all of humanity uses in a year. By accessing this energy, photosynthetic organisms could thrive wherever sunlight and water were available, far more abundant than the chemical energy sources that earlier life depended on. Photosynthetic organisms could simply outcompete other organisms, and they spread across the sunlit portions of the ocean. Second, and this is the part that changed the planet, photosynthesis produces oxygen. It's a waste product from the organism's perspective, but it's a highly reactive waste product. Initially, this oxygen didn't accumulate in the atmosphere because it reacted immediately with dissolved iron in the oceans. Iron normally dissolves in water when there's no oxygen around, giving the ocean a greenish color. But when oxygen is present, iron oxidizes, rusts, and precipitates out as solid particles that sink to the seafloor. For perhaps 1 billion years, oxygen produced by cyanobacteria reacted with iron in the oceans, gradually precipitating it out. This created the banded iron formations, layers of iron oxide alternating with layers of silica, some of the most distinctive rocks in the geological record. These formations are found on every continent, and they're billions of years old. When you look at them, you're seeing the rust stains of ancient oceans. direct evidence of oxygen being produced by photosynthetic life. Humanity mines these formations today for iron ore. Every piece of steel in modern civilization comes ultimately from the activity of ancient cyanobacteria. But eventually a tipping point was reached. Most of the dissolved iron in the oceans had been oxidized and removed. Oxygen produced by cyanobacteria began to accumulate in the water and then escape into the atmosphere. About 2.4 billion years ago, atmospheric oxygen levels began to rise significantly in what's called the Great Oxidation Event. This is not a sudden event by human standards. It played out over tens of millions of years, but it's sudden in geological terms. The Great Oxidation Event was probably the most consequential biological event in Earth's history, and it was also Earth's first mass extinction. Oxygen is toxic to organisms that evolved in an anoxic world. It's highly reactive, pulling electrons from organic molecules and damaging cellular structures. For anaerobic organisms that had dominated Earth for over 1 billion years, oxygen was poison. As oxygen levels rose, these organisms were driven into refugia, environments where oxygen remained scarce, like deep sediments or the guts of other organisms. Many lineages probably went extinct entirely. But of course, one organism's poison is another's opportunity. Oxygen also enables far more efficient energy extraction. When organic molecules are burned, oxidized completely to carbon dioxide and water, they release 10 to 20 times more energy than anaerobic metabolisms can extract from the same molecules. Organisms that could harness this energy, that evolved cellular respiration using oxygen, had an enormous advantage. They could grow faster, do more, compete more effectively. This set the stage for everything that came after. Complex multicellular life, organisms like plants and animals, require the high energy yields that only oxygen-based respiration can provide. Without oxygen in the atmosphere, you might have a planet covered in microbial mats and not much else. With oxygen, you open the possibility of complex life, of organisms with differentiated tissues and organs, of mobility and intelligence. But the Great Oxidation Event did something else too, something that nearly killed off all life on Earth. Methane, which had been abundant in the early atmosphere produced by methanogens, is itself a greenhouse gas, far more powerful than carbon dioxide. When oxygen rose, it reacted with atmospheric methane, removing it. This removed a major greenhouse gas right when Earth needed it most to compensate for the still dim sun. Global temperatures plummeted, snowball Earth and recovery. Imagine Earth from space 2.3 billion years ago. Instead of the blue planet we know, you see a white planet, ice from pole to pole, glaciers extending into the tropics, perhaps even reaching the equator. The oceans are frozen to depths of 1 kilometer or more. This is snowball Earth, one of the most extreme climate states our planet has ever experienced. And it may have been triggered in part by the rise of oxygen-removing atmospheric methane. There's evidence for at least 2, possibly more, severe glaciation events in Earth's history, the earliest around 2.3 billion years ago, and another dramatic series around 700 million years ago. The evidence comes from rocks that are definitely ancient glacial deposits, drop stones from melting icebergs embedded in seafloor sediments, scratches on bedrock from glaciers dragging rocks across them. And these deposits are found in places that were clearly in the tropics at the time, based on paleomagnetism. How did Earth get into this state? The precise triggers are debated, but the general mechanism involves a runaway ice albedo feedback. If Earth cools enough that ice begins to form at high latitudes, that ice reflects more sunlight back to space than dark ocean water does. This cools Earth further, allowing ice to advance toward the equator. More ice means more reflection, less absorption of sunlight, more cooling, more ice. It's a vicious cycle that can drive the planet into a completely frozen state. Once Earth is frozen, it should stay frozen, because ice reflects about 90% of incoming sunlight. The planet becomes like a mirror, and temperatures drop to perhaps negative 50 degrees Celsius average globally. This is cold enough that even carbon dioxide begins to condense out as dry ice at the poles. How could life survive this? And more importantly, how could Earth ever escape from this frozen state? Here's where plate tectonics saves the planet. Even under a global ice sheet, volcanism continues. Volcanoes punch through the ice and erupt, pouring carbon dioxide into the atmosphere. But now there's no liquid water to weather rocks and remove that CO2. The carbon dioxide cycle that normally regulates Earth's climate is broken. So CO2 just accumulates year after year, millennium after millennium, building up in the atmosphere. After perhaps millions of years, carbon dioxide levels reach extraordinary concentrations, perhaps hundreds of times higher than today. At this point, even though most sunlight is reflected by ice, enough is absorbed that the intense greenhouse effect from all that CO2 begins to warm things up. The ice near the equator, where sunlight is strongest, begins to melt. And here's where the feedback runs in reverse. Open water absorbs more sunlight than ice, which warms things further, which melts more ice. The deglaciation, once it starts, happens rapidly, perhaps in just a few thousand years. The planet swings from completely frozen to incredibly hot, perhaps with average temperatures reaching 50 degrees Celsius, far hotter than today because all that CO2 is still in the atmosphere and now there's no ice to reflect sunlight. It takes hundreds of thousands of years for weathering to gradually remove the excess CO2 and return Earth to more moderate conditions. The climate swings during snowball Earth events are the most extreme in Earth's history, and yet life survived. Microbial life is remarkably resilient. Even under global ice cover, there would have been refugia near volcanic vents, possibly thin films of liquid water at the base of glaciers, possibly small patches of open ocean maintained by volcanic heat. Life hung on, and when the ice melted, life exploded back across the planet. There's even speculation that the severe environmental stress of snowball Earth events might have accelerated evolution, driving the development of more sophisticated survival strategies that would eventually enable complex, multicellular life. What Snowball Earth teaches us is that Earth's climate system has tipping points, thresholds beyond which feedbacks can drive the planet into extreme states. It also teaches us that Earth has resilience, mechanisms for self-correction even from extreme conditions. But those mechanisms operate on geological timescales, millions of years. In the short term, on timescales relevant to individual organisms or even species, climate change can be catastrophic. This is a lesson worth remembering. By about 600 million years ago, Earth has finally stabilized into something recognizable. Atmospheric oxygen levels have reached perhaps 10% of modern levels, enough to support larger, more complex organisms. The climate has recovered from the last snowball event. Continents have assembled and broken apart multiple times through the action of plate tectonics, creating diverse environments. The stage is fully set for the next chapter in life's story, an explosion of biological creativity that would fill the oceans with strange and wonderful creatures. Life is about to get interesting. The Cambrian explosion. For 3 billion years, life on Earth consisted entirely of single-celled microorganisms. Then, starting around 2 billion years ago, the first tentative experiments with multicellularity began. We find fossils of simple multicellular organisms, just chains or mats of cells, nothing fancy. This continues slowly for over 1 billion years, with gradual innovations appearing. By about 600 million years ago, we find the Ediacaran fauna, strange, quilted-looking, soft-bodied organisms that might be early animals or might be something else entirely, evolutionary experiments that went extinct without leaving descendants. Then, starting about 540 million years ago, something extraordinary happens. Suddenly, in geological terms, over perhaps 10 or 20 million years, complex animals appear in the fossil record. This is the Cambrian explosion, and it represents the moment when Earth's oceans fill with animal life that we would recognize as animals, with eyes and mouths and limbs and shells and internal organs. The fossils from this period, particularly from a site in Canada called the Burgess Shale, show us just how creative evolution can be. There are trilobites, arthropods that look like large armored pill bugs and dominated the oceans for 300 million years. There are anomalocarids, meter-long predators with grasping appendages and circular mouths ringed with teeth. There are creatures like Opabinia with 5 eyes and a bizarre grasping proboscis. There are ancestors of modern groups like mollusks, echinoderms and chordates, the group that includes us. Why did complex animal life suddenly appear at this time after 3 billion years when it didn't? Scientists have proposed multiple factors that came together. First, oxygen levels had finally reached a threshold, perhaps 10 to 15% of modern levels, that could support the metabolism of large active animals. Animals need a lot of energy, and only oxygen-based respiration can provide enough. Before oxygen rose to sufficient levels, animal life simply wasn't energetically feasible. Second, the evolution of predation created an evolutionary arms race. Once some animals began eating other animals, there was intense selective pressure to develop defenses like shells or escape strategies like fast swimming. This drove rapid innovation in body forms. The fossil record shows shells appearing suddenly in the Cambrian, likely a response to predation pressure. Third, genetic innovations made rapid morphological evolution possible. The tool-kit genes, particularly the Hox genes that control body segment formation, had evolved by this time. These genes make it relatively easy, in evolutionary terms, to modify body plans, to add or subtract segments, or change the identity of body parts. With these genetic tools in place, evolution could quickly explore different body architectures. And fourth, environmental factors may have played a role. The end of the snowball Earth glaciations, 600 million years earlier, may have created ecological opportunities in a rapidly changing world. Continental configurations were creating diverse, shallow marine environments, shelves and lagoons and reefs where different species could evolve in relative isolation and then interact when ocean levels or continental positions changed. Whatever the precise combination of factors, the result is undeniable. The Cambrian explosion established most of the major animal body plans that persist to this day. If you look at animals in a modern ocean or on modern land, their fundamental architectures, arthropod, mollusk, chordate, echinoderm, were all established in that remarkable burst of evolution 540 million years ago. But Earth itself is still changing, still dynamic. While life evolves and diversifies in the oceans, the continents continue their slow dance across the planet's surface, driven by plate tectonics. And these continental movements shape the evolution of life in profound ways. Continents dance, climates shift. If you could watch Earth from space over the past billion years with time drastically sped up, you would see the continents sliding across the surface like pieces on a game board. They drift apart, pushed by new oceanic crust forming at mid-ocean ridges. They collide, crumpling and raising mountain ranges where they meet. Occasionally they assemble into supercontinents, giant land masses that contain most or all of Earth's continental crust. Then these supercontinents break apart and the cycle begins again. This is not idle geological trivia. The positions of continents profoundly affect Earth's climate and the evolution of life. Let me walk you through some examples so you can see how intimately geology and biology are connected. When continents are scattered around the globe, ocean currents can circulate freely, distributing heat from the equator toward the poles. This moderates global climate. But when continents cluster together into a supercontinent, ocean circulation is disrupted. The interior of a supercontinent is far from any ocean, creating vast arid regions, continental deserts on a scale we don't see today. The climate becomes more extreme, with hotter summers and colder winters, less rainfall in the interior. About 300 million years ago, the continents assembled into a supercontinent called Pangaea, stretching from pole to pole. The interior of Pangaea was one of the most extreme environments in Earth's history, a vast desert where temperatures could swing by 50 degrees between summer and winter. Life adapted by evolving strategies to conserve water and tolerate temperature extremes. This is when reptiles, with their watertight skin and eggs with shells, really came into their own, outcompeting amphibians that needed to stay near water. Continental positions also affect atmospheric carbon dioxide levels and therefore global temperature. When continents are positioned in the tropics with lots of rainfall, chemical weathering is maximized. This removes CO2 from the atmosphere and cools the planet. When continents are near the poles or in arid zones where weathering is minimal, CO2 can build up and warm the planet. The position of continents also determines where volcanoes form, and volcanism adds CO2 to the atmosphere. Different continental configurations create different balances between CO2 input through volcanism and CO2 removal through weathering. Mountain building, which happens when continents collide, also affects climate. Mountains intercept moisture from prevailing winds, creating rainfall on one side and rain shadows arid zones on the other. Mountains also expose fresh rock to weathering, which removes CO2. About 50 million years ago, the collision of the Indian subcontinent with Asia began raising the Himalayas, the highest mountain range on Earth. The intense weathering of these mountains, plus the fact that they disrupt atmospheric circulation patterns, has been implicated in the gradual cooling of Earth over the past 50 million years, eventually leading to the ice ages we're still technically in today. Continental positions also determine where life can spread and where it becomes isolated. When continents are connected, animals and plants can migrate between them, mixing genes and competing. This drives evolution as species encounter new competitors and new environments. But when continents separate, populations become isolated and evolve independently. This creates biodiversity through allopatric speciation, where isolated populations diverge into separate species. The classic example is the breakup of Gondwana, the southern supercontinent. When South America separated from Africa about 100 million years ago, the mammals on each continent began evolving independently. South America developed a unique fauna, including giant ground sloths, glyptodonts, and marsupial saber-toothed predators. Africa developed elephants, lions, and apes. When the continents eventually reconnected via Central America just 3 million years ago, species from each continent invaded the other in what's called the Great American Interchange. Many South American lineages couldn't compete and went extinct. Even today, continental drift continues. Africa is slowly colliding with Europe, gradually closing the Mediterranean Sea and raising the Alps. Australia is moving northward toward Indonesia. The Atlantic Ocean is widening while the Pacific is shrinking. Tens of millions of years from now, the continents will be in completely different positions, and that will create a completely different Earth, with different climate zones, different ocean currents, different opportunities and challenges for life. What you need to understand is that Earth's surface is not static backdrop for life's evolution. The surface is dynamic, constantly reconfiguring itself through plate tectonics, and life must constantly adapt to these changes. Geography shapes evolution, and evolution, as we saw with the oxygen revolution, can also shape geography by influencing climate and weathering patterns. Earth is a system where everything connects to everything else. The recent ice ages and human emergence. Now, let's fast forward to the last few million years, the most recent blink of Earth's history. But a period that's absolutely crucial because it's when we arrive on the scene. If Earth's entire 4.5 billion year history were compressed into a single 24-hour day, everything I am about to tell you now happens in the last few seconds before midnight. And yet these final seconds contain the story of our own species. About 2.6 million years ago, Earth's climate entered a new phase. The planet had been gradually cooling for tens of millions of years, ever since the Himalayas rose and began drawing down atmospheric carbon dioxide through weathering. But around this time, the cooling reached a threshold where ice sheets began forming on the northern continents. Not just mountain glaciers, but vast continental ice sheets like those covering Antarctica and Greenland today, but extending across Canada, Scandinavia and northern Europe. These ice sheets didn't form once and stay in place. Instead, Earth entered a pattern of oscillation between glacial periods, ice ages when the ice sheets expanded, and interglacial periods when they retreated. These cycles have repeated about every 40,000 to 100,000 years throughout the past 2.5 million years. We're living in an interglacial period right now, a warm spell between ice ages. The last glacial maximum, when ice covered its greatest extent, was only 20,000 years ago, which is barely a moment in geological terms. What drives these cycles? It's not changes in the sun's output or volcanic eruptions or any of the factors that caused earlier climate changes in Earth's history. Instead, it's something more subtle but beautifully regular. It's variations in Earth's orbit and rotation, what we call Milankovitch cycles, after the Serbian scientist who figured this out. Let me explain how this works, because it's a wonderful example of how astronomical factors can influence Earth's climate. Earth's orbit around the Sun is not a perfect circle, but an ellipse. And the shape of that ellipse changes over a cycle of about 100,000 years, sometimes more circular and sometimes more elongated. Earth's axial tilt, currently 23.5 degrees, varies between about 22 and 24.5 degrees over a 41,000-year cycle. And there's a wobble in Earth's axis, like a spinning top winding down that completes a full cycle every 26,000 years. This wobble changes which hemisphere points toward the Sun during which season. Individually, none of these variations changes the total amount of sunlight Earth receives by very much. But they change how that sunlight is distributed across different latitudes and different seasons. And that turns out to be crucial for ice sheet formation. Ice sheets grow when summers in the northern high latitudes are cool enough that not all the winter snow melts. Year after year, snow accumulates, compresses into ice, and builds up into continental glaciers. When the Milankovitch cycles align to produce cool northern summers, ice ages begin. When they align to produce warm northern summers, the ice melts back. These are not gentle climate changes. At the height of the last ice age, ice sheets 2 miles thick covered what is now Chicago and New York. So much water was locked up in ice that global sea level dropped by about 400 feet. You could have walked from Asia to Alaska across the Bering Land Bridge. Britain was connected to Europe. The coastlines were completely different from today, and the climate was far colder and drier, with vast areas of tundra and grassland where forests exist today. It was into this world of climate instability, this world of advancing and retreating ice sheets, that our species evolved. The hominin lineage, the evolutionary branch that includes humans and our extinct relatives, split from the other great apes about 6 to 7 million years ago in Africa. For most of that time, our ancestors remained in Africa, evolving in response to the changing African climate, which was becoming drier and more variable, turning forests into savannas. About 2 million years ago, some of these early hominins, species like Homo erectus, began migrating out of Africa into Europe and Asia. They encountered diverse environments, from tropical Southeast Asia to temperate Europe, and they had to adapt rapidly. But they were still quite different from us, with smaller brains and simpler tools and cultures. Our own species, Homo sapiens, anatomically modern humans who look like us, emerged in Africa only about 300,000 years ago. Think about that timing. Earth is 4.5 billion years old. Life has existed for perhaps 3.8 billion years. Complex animal life has existed for 540 million years. Our own species has existed for just 300,000 years, about 0.007% of Earth's history. We are incredibly recent arrivals to this planet, and yet in our brief time here we've done something no other species has done. We've developed the capacity to understand the planet that made us. For most of our species' existence, we lived as hunter-gatherers, adapting to whichever climate zone we found ourselves in, using fire and tools and clothing to survive in environments ranging from tropical forests to Arctic tundras. We spread across Africa, into the Middle East, across Asia and Europe, into Australia by about 60,000 years ago, and finally into the Americas by about 15 to 20,000 years ago, crossing that Bering land bridge during the Ice Age. By 10,000 years ago, humans had colonized every continent except Antarctica. Then, starting about 12,000 years ago, as the last ice age was ending and the climate was warming into the current interglacial period, humans in several different parts of the world independently developed agriculture. This wasn't a sudden discovery, but a gradual process of learning to cultivate plants and domesticate animals. But it was transformative. Agriculture allowed humans to produce more food from a given area of land, which allowed populations to grow and settle in permanent villages, then towns, then cities. Civilization, as we know it, with complex social structures and division of labor and written language, emerged from agricultural societies. And here we find ourselves today, 8 billion humans spread across the planet, having developed technologies that allow us to reshape Earth's surface, to redirect rivers, to level mountains, to alter the composition of the atmosphere. We've become a geological force. Scientists have proposed that we've entered a new geological epoch, the Anthropocene, the age of humanity, defined by human influence on the planet's systems. This brings us to a profound realization. For 4.5 billion years, Earth's story was one of geology and chemistry and physics. Then life emerged and began to influence the planet's chemistry and climate. Photosynthetic organisms created an oxygen atmosphere. Plants and weathering regulate carbon dioxide levels. But life's influence was generally slow and incremental, playing out over millions of years. Now, for the first time, a single species, our species, is changing the planet rapidly, on timescales of decades and centuries rather than millennia and millions of years. We're adding carbon dioxide to the atmosphere at rates not seen since massive volcanic eruptions millions of years ago, and we're doing it by burning fossil fuels, ancient solar energy that was stored by plants and buried over hundreds of millions of years. We're changing the climate, warming the planet, melting ice sheets, raising sea levels, acidifying oceans. We're altering the nitrogen and phosphorus cycles through agriculture. We're driving species extinct at rates that may rival the 5 great mass extinctions in Earth's history. We've become, whether we intended it or not, planetary engineers. This power comes with responsibility. We're the first species capable of understanding Earth as a system, of seeing how the atmosphere and oceans and ice and life all interact. We can study Earth's past and see how climate has changed before, what caused those changes, what the consequences were. We can make predictions about the future. And unlike previous life forms that changed Earth's environment accidentally as a byproduct of their metabolism, we have the capacity to make conscious choices about what kind of planet we want to leave for future generations. Earth survived the late heavy bombardment. It survived snowball Earth events. It survived massive volcanic eruptions and asteroid impacts, and the oxygen revolution that poisoned most life at the time. The planet itself will continue its geological evolution, will continue orbiting the Sun. But the question is, what will Earth look like? Will it be a planet that supports rich biodiversity and a climate stable enough for human civilization? That's up to us now. We're part of Earth's story, not separate from it. Understanding how Earth formed, how it evolved, how its systems work, this isn't just intellectual curiosity. It's essential knowledge for our survival as a species. Earth in perspective. Let's step back now and look at our planet in the context of its siblings, because understanding what makes Earth special requires understanding what went differently elsewhere. Our solar system contains 8 planets, and 4 of them are rocky terrestrial worlds similar in construction to Earth. Mercury, Venus, Earth, and Mars all form from the same protoplanetary disk. All were built through the same process of accretion and differentiation. And yet their fates could not be more different. Start with Mercury, the closest to the Sun. Mercury is small, only slightly larger than our Moon, and it never had a chance at habitability. Being so close to the Sun, any atmosphere it might have accumulated was blasted away by the intense solar wind. Its surface is scorched, reaching temperatures of 430 degrees Celsius during the day. There's no water, no weather, no geological activity to speak of. Mercury is essentially a dead rock, its surface cratered and frozen in time since the late heavy bombardment 4 billion years ago. Size mattered. Mercury was too small to hold an atmosphere and too small to maintain internal heat long enough to develop plate tectonics. Now consider Venus, Earth's so-called sister planet, because it's nearly identical in size and mass to Earth. Venus formed at about the same time from similar materials in a region of the protoplanetary disk, not much different from where Earth formed. Early Venus probably had oceans, maybe even plate tectonics. But Venus is just a bit closer to the Sun than Earth, receiving about twice as much solar energy. This apparently made all the difference. On Venus, more solar energy meant more evaporation from the oceans. Water vapor is itself a greenhouse gas, so more water vapor in the atmosphere meant more warming, which meant more evaporation, more water vapor, more warming. This is a runaway greenhouse effect, and once it began, it was unstoppable. Eventually, the oceans boiled away entirely. The water vapor rose to the upper atmosphere, where ultraviolet light split it into hydrogen and oxygen. The hydrogen, being light, escaped to space. The oxygen reacted with rocks on the surface. Without oceans to dissolve carbon dioxide, and without plate tectonics to subduct carbon-bearing rocks, all the CO2 that volcanic outgassing released just accumulated in Venus's atmosphere. Today, Venus has a crushing atmosphere 90 times denser than Earth's, composed of 96% carbon dioxide. The greenhouse effect is so intense that surface temperatures reach 470 degrees Celsius, hot enough to melt lead, hotter than Mercury, despite being nearly twice as far from the Sun. Venus is hell. A slight difference in distance from the Sun, combined with the absence of water to regulate carbon dioxide, made Venus utterly inhospitable. Now look outward to Mars. Mars is much smaller than Earth, about half the diameter and 1/10 the mass. Early Mars, surprisingly, was quite pleasant. We have strong evidence that Mars once had liquid water on its surface, rivers carving valleys, possibly even an ocean in the northern lowlands. The climate was warmer and wetter, probably sustained by a thick atmosphere rich in carbon dioxide, providing greenhouse warming. But Mars's small size became its doom. A smaller planet has less internal heat and cools faster. By about 4 billion years ago, Mars's interior had cooled enough that its magnetic dynamo shut down. The magnetic field that had protected Mars's atmosphere disappeared. Over the next few billion years, the solar wind gradually stripped away most of Mars's atmosphere. With less atmospheric pressure and less greenhouse warming, any surface water froze or evaporated into space. Today, Mars is a frozen desert with an atmosphere less than 1% as thick as Earth's. There's water on Mars, lots of it actually, but it's locked as ice beneath the surface and in the polar ice caps. The surface is too cold and the air too thin for liquid water to exist. Mars shows us that plate tectonics and a magnetic field aren't just nice features. They're essential for long-term habitability. Without plate tectonics to recycle carbon and regulate climate, and without a magnetic field to protect the atmosphere, a planet's habitability is on borrowed time. So what made Earth different? What allowed Earth to remain habitable for 4.5 billion years when Venus became hell and Mars became frozen? There's not one thing. It's a remarkable convergence of fortunate circumstances. Earth formed at just the right distance from the Sun, close enough to receive adequate warmth, but far enough that a runaway greenhouse didn't occur. Earth happened to be just the right size, large enough to maintain internal heat and drive plate tectonics and sustain a magnetic field, but not so large that it held onto a thick hydrogen atmosphere like the gas giants. Earth experienced the moon-forming impact, which gave us a large satellite that stabilizes our axial tilt and creates tides. Earth's interior differentiated with an iron core that remains partially liquid, generating our magnetic shield. Earth developed plate tectonics, which recycles materials and regulates climate over geological timescales. Earth had water delivered, probably during the late heavy bombardment, in just the right amounts. Not so much that we're a water world with no land and no way to regulate carbon dioxide through weathering, but not so little that we're a desert world. And perhaps most remarkably, life emerged on Earth and transformed the atmosphere through photosynthesis, creating an oxygen-rich atmosphere that could support complex organisms. This didn't happen inevitably. Earth was habitable for over 3 billion years before oxygen levels rose high enough for complex life. If photosynthesis hadn't evolved, or if it had evolved but oxygen never accumulated for some reason, Earth might still be a world of nothing but microbial mats. We wouldn't exist to tell this story. When you consider all these factors, you realize how special Earth is. Not necessarily unique, the universe is vast, and there are likely billions of planets around other stars, but special nonetheless. Every condition had to be right. Earth is a world that works, a finely balanced system where geology and chemistry and biology all cooperate to maintain habitability. But Earth's story isn't finished. The planet continues to evolve, and we can make predictions about its future based on what we understand about its systems. The Sun is gradually brightening, about 10% per billion years. In perhaps a billion years, maybe a bit more, the Sun will be bright enough that Earth's oceans begin to evaporate significantly. Once water vapor accumulates in the atmosphere, the greenhouse effect will intensify. This will trigger the same runaway greenhouse that killed Venus, and Earth's oceans will boil away. Earth will become uninhabitable for life as we know it. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core and begin fusing helium. It will expand into a red giant, perhaps 100 times its current diameter. The Sun's outer layers may actually engulf Mercury and Venus, and quite possibly Earth. Even if Earth's orbit drifts outward enough to avoid being swallowed, the planet will be baked to a cinder, its surface molten, its atmosphere stripped away, everything we know incinerated. Eventually, the Sun will shed its outer layers, creating a beautiful planetary nebula, and its core will collapse into a white dwarf, slowly cooling over trillions of years. Earth, if it still exists, will orbit this white dwarf as a frozen, lifeless cinder in the darkness. That's Earth's ultimate fate, dictated by the life cycle of the star that gave it birth. This might sound depressing, but I want you to consider it from a different angle. Earth has hosted life for at least 3.8 billion years. It will likely remain habitable for complex life for at least another 500 million to a billion years, possibly longer. That's a total lifespan of about 5 billion years of habitability. That's extraordinary. That's enough time for countless species to evolve, flourish, and contribute to the story of life. That's enough time for intelligence to emerge, for consciousness to arise, for beings like us to appear and contemplate the cosmos. We exist in what might be called the golden age of Earth's habitability, a time when the planet has liquid oceans, a temperate climate, an oxygen atmosphere, continents and oceans creating diverse environments, a biosphere of stunning complexity. This won't last forever, nothing does, but that makes it all the more precious, doesn't it? We're here now, in this particular moment in Earth's history, lucky enough to experience this world while it flourishes. And here's the most remarkable thing. 4.5 billion years after forming from a cloud of gas and dust, Earth has produced creatures capable of understanding their own origins. We can look at ancient rocks and read the history written in them. We can peer into the cosmic distance and watch other planetary systems forming around other stars, seeing the process that created our own world happening elsewhere. We can run computer simulations and mathematical models and figure out how planets form, how climates evolve, how life emerges. Think about what this means. We are the universe becoming conscious of itself. We are atoms forged in dying stars billions of years ago that have been assembled through billions of years of planetary evolution into patterns complex enough to wonder about their own existence. The iron in your blood, the calcium in your bones, the oxygen you're breathing, these atoms have been on a journey lasting longer than you can easily imagine. They were created in stellar explosions before Earth existed. They were part of the cloud that formed our solar system. They were incorporated into planetesimals that collided to build Earth. They've been cycled through volcanic eruptions and weathering and erosion, through the bodies of countless organisms that lived and died, and now, temporarily, they're part of you. You are not separate from Earth's story. You are Earth's story, a chapter in an epic that began 4.5 billion years ago in a disk of gas and dust, and will continue long after any individual human has returned to dust. Every breath you take connects you to the ancient cyanobacteria that first produced oxygen. Every heartbeat pumps blood, whose iron was made in an exploding star. Every thought you think happens because of the complex chemistry that only became possible after billions of years of planetary evolution. This is the story of how Earth was formed. It's a story of cosmic violence and patient construction, of accidents and inevitabilities, of disasters and resilience. It's a story where chaos gave rise to order, where simplicity evolved into complexity, where bare rock became a living world. And it's a story that includes you, that led to you, that continues through you. So the next time you look up at the moon in the night sky, remember it was born from a collision that nearly destroyed Earth. The next time you feel the solid ground beneath your feet, remember you're standing on a thin crust, floating on an ocean of molten rock. The next time you take a breath, remember you're breathing the waste product of ancient microorganisms that transform the planet. The next time you see a mountain or an ocean or a forest, Remember, you're seeing the result of 4.5 billion years of planetary evolution. This world, this beautiful, complex, dynamic world, this Earth that we call home, formed from the dust of dead stars and evolved through processes we're only now beginning to fully understand. It has survived apocalypses that would have ended lesser worlds. It has hosted life for nearly its entire existence, nurturing that life through ice ages and asteroid impacts and volcanic catastrophes. It has produced intelligence and consciousness and culture. Earth is not eternal, but while it lasts, while it maintains this incredible balance of conditions that allows oceans to flow and forests to grow and creatures to thrive, we have the privilege of being here to witness it. We have the responsibility to understand it, to appreciate it, to preserve what we can of its wonder for whatever time remains. That's the final lesson of Earth's formation story. We are not masters standing above nature. We are participants in Earth's ongoing story, one species among millions that this planet has created, distinguished mainly by our capacity to understand the journey that brought us here. The same forces that built mountains and carved canyons and filled oceans, those forces continue today. Earth is still evolving. The story isn't over. And now you know how it began. From a cloud of cosmic dust to a molten protoplanet, to a world of fire and bombardment, to a water world where life emerged, to a living planet with oxygen atmosphere and complex ecosystems, to a world where one species finally evolved the ability to look back through time and understand its own origins. This is how Earth was formed. This is how we were formed. This is our cosmic inheritance, our planetary home, our only world. Take care of it, understand it, appreciate it. Because this world, this Earth that took 4.5 billion years to make, that survived countless catastrophes and threaded countless unlikely needles to become habitable, that created you through an unbroken chain of evolution stretching back to the first living cells, this world is precious beyond measure. And for now, for this brief moment in cosmic time, it belongs to us all.